Hello everyone, so this is Jagriti and welcome to the second week of this NPTEL weekly session. I'm a PhD student at IIT Gandhinagar and this is Sunday morning, 10:30. So I don't expect everyone to join, but of course I'll just go through what we discussed previous week and we'll give a 10-minute buffer in between to see if more of you can join if you have that bandwidth to join today. And give me just like 10 minutes or so, something till the time people join. I'll just set up my tablet and the mode to screen share and all. So today we'll be speaking about sensors and oh, sorry, I forgot to introduce. So I'm a TA for this NPTEL course that's Biomedical Instrumentation by Professor Balajan from IIT Madras. And this course is very essential for all students who are working on in the field of biomedical engineering, doing some mechanical engineering. It's sort of a UG plus PG level course. You can always take it whenever. 2 minutes. Yeah, so whenever you sorry, it's a UG level course, and you can always take it whenever you want. You are willing to learn more into this biomedical instrumentation side, or you want to work at the intersection of healthcare and hospitals to know how these sensors work and how these principles work. So, of course, for biomedical engineering students who are doing their bachelor's, they do have this internship at the end of their fourth year or in between their 3 and 4 years also. Now, I guess it's mandatory through institute norms that you need to do. Well, in that, 2 minutes, huh? Yeah, so in that you should sorry. No, yeah, you go to hospitals, you take their permission, and then you see surgeries which are being involved. Let's say if you are a biomedical engineer and in future you want to work in hospitals or R&D sector or something, then you need to know this instruments and equipments very thoroughly so that you can directly go and join them. Now, the thing is not to only know them, but to also understand that which particular physiological parameter we are trying to measure using so, and that physiological parameter, the settings of it, the its response with respect to the human body, which sensor should be used, should it be broadband, wide, like narrow band, the sensor range limits, all those things are then concerned later. Also, like knowledge of these things is what this course will teach you ahead. Okay, so I'll just share my screen quickly and we'll begin. Okay. So, of course, anytime you have any queries, you can always join the sessions and interact lively with me. Or you can post comments on the YouTube platform or on the NPTEL platform also. So, you have in like now, SWAM is currently being updated, or what the portal I'm seeing is not the one that I was used to. So, but there would be a page called as announcements and post your query or something, discussion forum, so you can always go there and post your queries on there. Either me or one of the NPTEL TAs, like TAs from Professor Varadhan's lab or his group or the students that he might be teaching, would be the ones replying to your query. So we can always solve your query there also. If you have any questions related to assignments, you have questions related to the course content, any particular points in within the week that you don't understand, you can always post them there. Okay. Well, this is very important for people who are willing to take the exam at the end of this 12-week course. So that's why you should be concerned with doing the assignment hours and following it. Okay, let's share the screen now. Okay, I hope my screen is visible now. Yes. Okay, so let's begin. Let's just have a brief overview of what the last week was about. Uh, Yes. Yes, so if it's visible to all of you, let me do this in landscape mode. So last week we began with sensors and transducers and why, I guess let me enable mic access to people who have joined. 2 minutes. Okay, so I guess you can unmute yourself whenever you want. You have a query or something, and then you can always raise your hands if you want to ask a question. Any way works for me. Well, this is a one-time shared link, so I don't think so you'll be able to chat here with me. But of course, you can unmute yourself and speak lively with me. So let's make it an interactive session, okay? So the first week was all about sensors and transducers, how different physiological phenomena, different signals are, and then we looked at the human body, which particular signals are important there. Is sensor a type of transducer or transducer a sensor? What's the difference in between actually both of them? The transduction principle. Then we looked at this for three basic terms that were specificity, sensitivity, and stability, which are very important. And of course, why accuracy is not equals to precision and how they both are different from each other. Okay, then we looked at different characteristics of sensors and transducers, like what is actually needed whenever we try and make a measurement system, how compact the system should be, what type of noises should be suppressed in that system, different types of biopotential electrodes and the signals that we receive from them. The signal, if it's a weaker signal, so how do we amplify it? For amplifiers, we looked at op-amps. Then for noise, we looked at different filters to filter out those noises. So we had a measurement system that, okay, we have an object of measurement, we have a sensor, then an electronic instrument as an amplifier, and then we'll observe it through our display. There were different characteristics of these systems, like one was a static and another was a dynamic system. So we looked at linearity, sensitivity, resolution, hysteresis, reproducibility, threshold, the key characteristics of all systems which are needed. Of course, a system which resonates at its own central frequency, we don't want to excite it at that frequency and excite it at a lower frequency so that the output is being resonated at it. So it helps us to prevent the distortion and remove the undesirable signal. The dynamic or transient characteristics are like as that of time constant and frequency response of your system. Then we had looked at different linear and non-linear systems. One which show us an output which is cumulative difference of all, whereas the non-linear ones which are like have a component of harmonics, different frequencies in them, change in amplitudes. And then if you're able to analyze a system in its analytical domain, that meaning that if you're able to see a system in the time domain waveform, that time versus voltage, and you just analyze it there, but instead this time domain of it does not give you that much information about the physiological signals that are varying with respect to frequencies or the smaller peculiar changes that are being happening in your body. So for that you look at the nonlinear spectra, and for that to like exploit it, you do frequency response. This is being done using Fourier decomposition. We didn't go much deeper into it, but of course you can always read about FFT, fast Fourier transform, then there's discrete Fourier transform. This all you can look into digital signal processing. So and like analog and digital signal processing, there you'll have idea of both of them. And there are like different types of systems: first order system, second order system, how you overshoot the errors, reduce the errors, transient errors. So in time domain, we saw that, okay, if we have a step function and we see how much time it takes to saturate it, there were times which are concerned with it. One as response time and one as settling time. Okay, then there's amplifiers, one of the like from 1990s, which has been going on the most known one and most popular one is the operational amplifier op-amp. So that being said, you also have an IC of that op-amp 741. It has a high gain, it's a direct current differential amplifier, so you have multiple stages of it to also make it as a adder, subtractor. Those things are there. So this using this type of amplifier, you can always amplify your weak physiological signal, and instead at the towards the end you can convert it back to an electrical quantity so that you can process it using digital signal processing and methods. Okay. Yeah, of course, you have the bandwidth of your entire system where you work with. Now, this bandwidth is also divided as you take always a 6 dB bandwidth or you take a 3 dB bandwidth. Now, based on this criteria, you look where your frequency response or system is more sensitive at. So when you plot your frequency response, that might look something like this. So the thing where you take, so this is your amplitude level, where you take this full width half maximum or full width half maximum. Oh, sorry. Or here, I'll just plot it. Yeah, okay. So the point where you take a full width half maximum, meaning that you're concerned with the entire thing, whereas half maxima is like entire power by two. So these are like the two metrics which people usually use when they define the bandwidth of the system or the power which is being utilized by the system. So for which we use these two systems. Of course, when you deal with amplitudes, it is different. When you deal with power, that square of it, it is different. Okay, so both terms vary accordingly. Okay. And then there were filtering techniques. So which type of noise which is there occurring in our system. So of course, here we are talking about biomedical instrumentation and the signal that we are measuring as our physiological human body signal. So that noise has very that signal will have a very high intrinsic inherent noise. And that noise you cannot always suppress. Like you don't know if the frequency at which your noise is being occurring can be the frequency at which your signal of interest is also happening. So there are like noises which are categorized into these four: thermal, flicker, interference, and artifacts. So you have different filters for them. You have a low pass filter which helps you to cut off, like helps you to retain the frequencies till your cutoff frequency, this FC, and after which it will remove all those frequencies from your system. Then you have a high pass filter, like till the point it will remove all the frequencies, and after that point it will help us retain the frequencies. So these filters are like ideally in a theoretical scenario, you might say that okay, this filter is suppressing this much. So for a low pass filter, it is this, or for a high pass filter, it is this, or for a band pass filter, it might be something like this. But practically, like in real life, you're not able to achieve this very strong step functions. Okay, so it's always either exponential or either Gaussian kind of. So what you're trying to achieve in this case is like okay, for a low pass filter it might be like this. So your response decays over time, it will filter out over time. So it is usually following a Gaussian profile because the noise which occurs in this physiological signals always have a Gaussian noise in them. And this Gaussian noise we also term it as white noise. Okay, so it comes from there. Again, for a high pass filter, the thing can be like this. It starts following from this point. For a band pass filter, it would be like this. So it's only passing in between these two. For a band reject filter, it can be only this small narrow band that it's allowing it to pass. A notch filter is like it will only retain one specific frequency and then it will allow all of them to pass. So like there are these different kinds of filters and how their responses can be modeled. So these filters are simple LC based circuits, say LC-RC circuits. You can have a combination of resistor, capacitor, and inductance and make a filter by yourself in lab if you have access to. Okay, so this is all we had in week one. Then we went through its assignment. Of course, till now you might have been, you already have the due date of the assignment gone. So you might have done this assignment before. So this assignment belongs to previous week. So there are like 10 questions based on transducers, smart sensors. We had amplifiers, accuracy. So yeah, you always need to look at different terms and what your question is really trying to ask you to. So this question had everything, but the question that it asked us was what accuracy really means. So the definitions for all of them are very close and very net bounded to each other. So you really need to know the exact difference in between them. If you don't know, then you're definitely tied up in between accuracy and resolution or accuracy and precision. So you won't actually get the differences in between them. For a dynamic system and for a static system, it's better if you go and understand the key characteristics of them, how they differentiate, how noise in them varies, how the input impedance should be. So those things will be clear if you read about op-amp also. Okay, this was there. Then there's like, okay, low pass. So you see, questions are so simple. So you have a low pass filter, it will only allow low pass frequencies and block the high frequencies. So whenever you have an exam coming ahead for the 12-week course, you'll always have questions like this only. Okay. Biopotential electrodes are used for like to convert an activity from one. So it's always a electrical signal being converted from the physiological signal that is being measured. So it always is a case matter of thing that what is your measurement and what's your measured quantity. Okay. So these are the two things that this entire instrumentation revolves around. Okay, then we had like what type of noise had a uniform. So of course the noises and everything that's not in the lecture notes, but during the lecture I talked about it because time was very less. So how we and then okay, then there were different types of noise and then hysteresis. So how we usually do this is okay, we'll go through the lecture sessions, lecture weeks, what profs taught in the online courses. I'll try to cover all of them, but if time does not permit because this is like a 2 hour session, so what I'll do is like last 30 minutes, I'll always reserve for the assignment questions for you to solve the questions efficiently that you have in due. And the questions that I'll be solving is previous years ones. I am allowed to what did I say? I'm allowed to discuss the current year question also with you, but I cannot tell the direct answers. And there have been cases where students tend to ask these questions. So, okay. And yeah, whenever a lecture or something is missed out, okay, let's say we are able to do like 3 lectures in a week and prof had taught like 4, 5, sorry, like double of them or something, then we'll always carry it forward and do it in the next session. But of course, we'll cover the assignments before the session ends. Okay, that would be my foremost priority to complete the assignments also and to discuss those questions. Okay. So today, like since we have covered everything about sensors and transducers, I hope this is visible. Yes. So we'll be talking about basic type of sensors, different sensors which are available there in biomedical systems and their own principles. So to begin with, like there are different resistive, inductive, capacitive types of sensors, and then a piezoresistive, so piezoelectric sensors. So the gist of all of it you might know till now. There are like some like very small details into it that probably you should remember them, but they are like more from material side. I don't know numbers as such that the sensitivity factor or gauge factor or material properties in a way would be asked, but if they are, probably you can remember something for which are like very well known or which are well used in applications. So for or let's say for ceramics, for quartz, for silicon, the ones which are very standard, platinum, constant. And so some of them you can always remember, but not for all. So, you know, right, how capacitor permeability factor, we know resistance, we know temperature, but there are some things. So probably this course needs you to, I don't think so you should, but we'll see as in how we go through coming up weeks that if there are some questions like this which involve you to remember certain terms or not. Okay. Yeah, so first we'll again start with the same thing that is a sensor. So, of course, people who have joined, you can always unmute yourself and speak up. Is a sensor a transducer? So, is this way, is it correct, or is this way, is it correct? Which way follows? Anyone? I hope I'm audible.
Sensor is a type of transducer.
Yes, exactly. So, sensor is a type of transducer. Like we can say that it's a subset of a transducer.
As a sensor, but not all sensor is a transducer.
Exactly. Yeah, very well said. But not all transducers are sensors. So the basic difference in between them is a sensor is able to detect a physiological signal and it always converts it back to an electrical quantity, whereas a transducer works on a transduction principle and it helps us to convert from the important term here is convert one form of energy to another form of energy. So it can convert a acoustic energy to a mechanical energy, electrical energy to an acoustic energy, those form of things it can do, and then vice versa further it can work on. Okay, so sensor is a subset of transducer, but not vice versa. Yeah. Yeah, that being said, we have different types of systems. So in analog signal conditioning systems, you have sensors, or sorry, so you will have sensors. You have gauges. So here, the one that we are talking about are the one strain gauges, which works through resistive principles, through change in their resistance or the effective deformation in the particular sensor, you get a response to it. The electrical quantity is being generated. So these work using resisting resistor based sensors. Okay, and then there are also different, so one being this, then there are something as charge based amplifiers. And these charge based amplifiers work on the principle of storage. So, being storage, being said, is something in our system which stores something is a capacitor, right? So, capacitive based systems, which helps us to charge at a time and also discharges after a time. So, something like that. Okay, then there are different filters that we talked previously, but I guess this session does not have those. And then for calibration, all of them like, okay, to work on a physiological signal, your system should always be calibrated to a reference spirit level, to ambient pressure, to temperature, and so that only you can reference that particular value to the actual human's measurement that you're trying to do. Okay, so for resistive basis, you have like different two, three types of it. You have strain gauges. Okay, so let's let this be SG. And then you have something that is called as thermistor. Okay. So the material differs, the temperature that they are trying to measure also changes. The sensor is also different. The range in which you can do those measurements also changes. Okay. Then there are capacitive sensors, which are like pressure based displacement, right? Change in capacitance will help us to map the pressure, vice versa. Similarly, the displacement also, since capacitance is directly proportional to the displacement of the plates which are being moving apart from each other. Then you have inductor. So you have inductive based. So in inductive based, you have like multiple principles. You might have a single inductor, two inductors together, or something which works on a principle of differences in between both of them. So if you have a simple one, a single one, that's self-inductance. If you have two, so it monitors its position with respect to the relative position of another one. So that's mutual inductance. If you have two or more than two, let's say, you have a variable differential transformer. So in that case, that thing, so it changes with respect to the, so one of them is your primary system and two other are your secondary system. So if the primary system changes, the two will change mutually in between both of them. So it also has a principle of self-inductance and a principle of mutual inductance governed. Okay. So in this, if you might want to say, is the sensor a subset of them is LVDT, that stands for linear variable differential differential transform. Okay. So these are there. And then you have some piezoelectric sensors. I guess for today's session, we'll talk about resistive, capacitive, and inductive sensors, and then we'll do the assignment. So after that, there are only like piezoelectric sensors, so electric, resistive, those sensors are there. So what these do is like they have a crystal in them, and that crystal essentially helps us to convert from one form of energy to another. It's essentially measuring the mechanical form of energy there and converting it into electrical. That mechanical form of energy can be a displacement force, pressure, and so on. Okay, so in this type, you might have some force sensors, you might have some vibration based sensors. Of course, like there's a part of this piezoelectric sensors, so which is also involved in to ultrasound. So sorry, US. Sorry, into ultrasound. So what happens in there is you measure a mechanical signal, and that mechanical signal is being converted back to an acoustic quantity, and that acoustic quantity is being converted into an electrical signal. So now using that electrical signal, you can do your fourth and measurements. Of course, then the other way follows that if you send a transducer an electrical signal, that electrical transducer will sorry, that signal, the transducer, it itself has a membrane and a focusing lens. So then it will pass on it, and that signal when it interacts, so that's an acoustic quantity. That acoustic quantity or the signal when it interacts with the subject that you're trying to measure its property through, then it will again hit the transducer back. If it's in, let's say, a pulse echo setting, like you are only using one transducer at a time. So you're sending through it and you're again receiving through it at the same focal point. And then it will convert, this sensor will again convert the form of energy into electrical energy. Okay. So in ultrasound also we use those. So there are like types of it. We use quartz, we use PZT, we use PVDF, polyvinyl difluoride, and then we have a sorry, zirconate, titanate, things like that. Okay, so we have different sensors in ultrasound also for these to measure. So the transducer incorporates this type of sensors. Okay, this type of crystals in them so that we can convert this form of energy and have this transduction principle. Then following this inductive thing, we have effect known as Hall effect. So it's essentially based on the magnetic field, how it changes, the differences occur. So it's dependent on the magnetic field. And then you have sensors which vary with respect to the pH of the system. So something as electrochemical sensors, something that chemical engineering people often do. They do electrolyte studies, they do this pH based studies. Even bio people do those gel electrophoresis. They measure the impedance differences across two electrodes, measure the DNA polarity and those things. And then you have like optical sensors. So these are like how changes in the sorry, the incident light, how it changes. Based on it, the resistance of that material will change, and hence how your output electrical quantity will change. Any questions? I guess not. Okay. Yeah. So the sensor, this actual word, it has a Latin root. Okay. So that just means, so sensor stands as to sense something. So it comes from a word which is called as perceive. Okay, so same thing that we just looked. So the actual thing that a sensor will do, it will just detect a signal within our human body, a physiological signal, and then it will convert back to an electrical quantity. So never confuse a sensor with a transducer. Okay, and then there are like different sensors. So you will have a barometer to measure pressure. You have a thermometer, right, to measure temperature. You have a photoresistor. Like at times, people also have these photoresistors in their house next to their plants so that they can say that see how much energy or photosynthesis is being trying to occur. If they have plants who require very less amount of light and equal amount of water, so these kind of things also people do. You also have those UV lights, UV chambers. Okay, so these are like something which are directly proportional to light, and this proportionality to light changes the resistance there, and this resistance changes further the output quantity that we are trying to measure. Okay. Then in vehicles or systems, you also have something which is called as accelerometers. You also have those in your phones nowadays, that you have these accelerometers and gyrometers through which you can measure the angle at which your phone is kept, or it changes accordingly. You have a dynamometer, you have a magnetometer, like we have wireless chargers nowadays, so you can always check into to that point. Okay. So sensors are everywhere, of course. Transducers are also everywhere. So let's begin with the resistive sensor first. Okay, and then we'll go on ahead. So before that, I guess I can also tell you something about. So, like I work in ultrasound field, so most of my knowledge comes from there, and my references would also be from there. So there's this open source startup that's called as Wooplus, most likely this or something like this. So it's like a wearable ultrasound system, pulsar receiver system. So you have only this small chip that's the size of a coin, and in that particular chip you have everything. You have a transducer, sensor, piezoelectric sensors, crystals, one to convert form of energy, one to generate a source of supply. Everything you have in a source of chip, which is like as small as your 1 rupee coin. Okay, and what they do is that this is now wearable, so you can have it like wear it wherever the point of interest or signal of subject of interest is, and then you can measure the appropriate electrical quantity from there. After that, people have this scaffolds. Okay, and nowadays they have these smart sensors which are integrated in the scaffolds. So you have applications as wound healing. Okay, or continuous needle based drug delivery. Now, what is this? This is actually where you'll have a small patch, and this patch you'll have multiple small needles. These needles can be as small as 1 micron, okay? Can also vary as 10 microns based on the type of drug that they are trying to deliver. And this one inserted to your skin, it will release all sort of chemicals which it needs to permeate this our skin membrane at first, and then it will deliver the drugs to the on-site where they want it to. And this only works very timely. How timely is like now these needles and sensors are also processed or are placed in a form an array. So at time only one range will limited, then another will be limited based on the thickness of your skin. So that's how smart processing even people who are there in biomaterials nowadays are also able to do. Okay. So these are something which comes under the field of injectable gels or hydrogel, something like those. Okay, now back to our biomedical instrumentation. We'll first look into resistive sensors. So you can ask any questions whenever you have at any time. You can interrupt me. That works for me. Okay. So with resistive sensors, the first one that we see is strain gauge. Okay, so judging from it, the strain gauge can be a metal, can be a semiconductor. Okay, these things are very important. You need to know that what form it naturally comes into or it's naturally synthesized from. So now this comes into a metal or conductor, semiconductor. What happens in here is when it is stretched. So if let's say you have a material like this, which has its original length of x, and now this material you're stretching it to this point. Now it has been stretched to a material of delta x. So how you define a strain? A physical quantity is change in length by the original length. So that's your strain. Okay. So this is the strain I gave to this particular metal or semiconductor film or whatever this wire I had. And that is within its elastic limit. Okay. Because after this limit, the strain won't be strain itself because the material will enter into the regime of plasticity. Okay, so it won't recover back its own shape. Strain is when if you try and deform a subject within its elastic limit so that it can deform back to an original place. So let's say I'll just give you a very trick question. Is rubber more elastic or stainless steel more elastic?
Stainless steel.
Exactly. Would you mind telling us why?
Because we move rubber, it will go one certain time, it will break. But stainless steel go long elasticity.
Exactly. And people think that it's very rigid, and that's why it's rigid. It's not elastic, but the thing is something else. Now you're trying to retain its elasticity within that particular regime, so it won't break off to that point. So SS is more elastic than rubber band. Okay. Okay, so we define resistance as rho L by A, and if you try and see the differences in the resistance with respect to the unit, you'll have see it as like now here you're basically trying to see the differences. Okay, so this works on first order differential equation. Okay, so how you do is like you just take partial differences in between the variables that you see. The ones which are multiplied in the numerator are added, whereas the ones which are in the denominator will go to numerator and will have a negative power to them, right? So will be subtracted from the terms. So plus you have for length, and then minus you have for area. Okay, so this stands for your density, length, and area. Okay. Now with it, you have different types of strain. Let's just first derive the Poisson's ratio relationship with it, and then we'll look forward. Okay. So area, you can also define area as width times thickness, right? So you can write it as del A by A equals del W by W plus your del T by T. And we just looked at that what strain is del X by X, right? So any deformation in a quantity with respect to its original length. Okay, so this is like equal terms. So these you can write it as 2 times of effective change in strain either in transverse direction or longitudinal direction. Let it be in one direction for now. So this is very simplistic version of it, but there is a term called as Poisson's ratio. Now what happens in this Poisson's ratio is if you stretch a material, the length of the material will increase, but the thickness of the material will decrease, right? So material is being stretched, the length increases, width, thickness, it will decrease. So same thing, the one which increases are assigned with a positive sign, ones which decreases with a negative sign. So you define this Poisson's ratio as negative of your transverse strain in your transverse direction. So your transverse direction is where your particle displacement is perpendicular to that of your original excited displacement, okay, or excited pressure or any like type of force that you are exerting on the material, divided by your longitudinal one, because it's actually like originally in the same direction of particle displacement. Okay, so here, now if you look at these ones, which we directly wrote it as 2 times of strain, now this is nothing but width is decreasing. So this is minus of, so your this transverse strain, right? Because width is in following in the transverse direction. So it would be your Poisson's ratio times your longitudinal strain. So this is negative of Poisson's ratio times longitudinal strain. Thickness also follows in the same pattern. So you have again negative of this and this. So if you assign these with the sign, these are actually minus 2 viscosity, your Poisson's ratio times your longitudinal strain. So not this one. So this one is actually wrong, whereas this one is actually correct. Okay. Then, if you have this Poisson's ratio, let's go back to this resistance relationship. Delta R by R is equals to your delta rho by rho. Well, it won't change. Your delta L by L will become what? Any guesses? Will it have a positive sign or negative sign? So your length is increasing, right? So it's a sign with a positive sign. So you have it with your coefficient, your strain increases, so your length increases, and then you have minus of del A by A. So minus of, and then you have minus again, like this. Okay, so you have rho V, rho by rho, plus you take this outside, and you have this 1 plus 2 mu. Okay, so this is a relationship that we had in the lecture slides also, where this is your Poisson's ratio. This is your longitudinal strain. This was had a positive sign because length increases whenever your material is strained, and these had a negative sign because width and thickness essentially decreases for that material. Okay. Now with this relationship, you also have a factor which is called as a gauge factor. Okay, and you look for this gauge factor. In a way, it helps you to monitor real-time measurements, real-time diagnostic measurements. It works as an gain, so to an amplifier, that how much you should increase it so that your differences or changes do occur. Okay, so it's a very sensitive term. So it is defined as change in resistance over your strain. Okay, so you can write it again as your G times strain is delta R by R naught, and hence you can again differentiate this thing. So you have this as 2, and you can like substitute this in terms of here. So you can write it as again as your gauge factor is equals to, and so this would be cancelled and you'll have 1 by rho here, right? So you have 1 plus 2 mu plus you have 1 by your strain times your ratio of density. Okay, so this is another such derived equation that you have. So you don't need to remember these, um, what do you say, these relationships. You can always derive it beforehand whenever you need those, but I don't think so you'll need this whenever solving any questions. It's just for your simplicity, for your sake of knowledge. Now, these gauge factors, they are like in catheter tips, okay? We have them in catheter tips so that you can insert it into a very small needle or mounted sensor, and you can go measure the real-time diagnostics, how much pressure is being changed, temperature is being changing. So it's also being used in intra arterial, or you say in intravenous, whenever you have IV. So you go and you have those glucose saline being taken. So all in there, the pressure monitoring and sensor is being done. And like big hospitals, like multinational hospitals and those, like there isn't one nurse after each table, bedside nurses. So what they have is a sensor which is in their IV line, which tells them at the nurse station that okay, this person's line is almost about to complete. So they have a threshold sensor to a point, and that will alarm them. And after accordingly, they come and they'll close the knob in those, because now you don't want air bubbles to inject into your blood, and those air bubbles will eventually cause clots, heart attacks, and whatnot. Okay. Okay, so with this, another thing that you should also know is something that Prof talked about was Wheatstone Bridge. Well, of course, it was mentioned in class that you should always go and look at that. But I don't know if many of you know about it or not. So for simplicity's sake, I'll just give a very brief introduction into Wheatstone Bridge also. I hope it's visible. Okay. So what a Wheatstone bridge is, it came through Charles Wheatstone, like following his name, and it helps us to find the voltage potential difference in between two points of interest. It also helps us to find known or unknown resistance, what it takes to make a bridge balanced, unbalanced, those form of configuration we can know from there. Okay. And this has also been incorporated into small circuits and systems to make them system parallel and balance them. Okay. So you have this main source of supply. Sorry, it's not drawn to scale. Let's say this is your source of supply, and these are like 2 points. Let's say this is A and this is B. Then you will have a diamond shape here. Okay. And across this, you have, let's say, these 2 points, let's say C and D, through which you measure a potential difference at. So this is your VCD, or you can also write it as just as a voltage source in between both of them. Okay. Now this, let's say, is your resistance R1, can be your R2, can be your R3, and can be your R4. So if you want to find, let's say, the value for this resistor, this R4, I guess it's not visible. Okay, let's say if you need to find the value for this R4, though we can have it as named as Rx, okay, and this R3 accordingly would be adjustable then. So something as it can act as a potentiometer. Okay, that means the resistance can be adjusted. Okay. So what happens in here is you assume you can like make it or split it up to for ease of your understanding. So this can again be shown as, let's say this is now not, let's say, first point of contact was A, first point of contact here was your B, right? Now you see what do you have in between A and B? You have a point of connection of C, right? So you can always make it like this, right? So you have your R1 and you have your R2. And then something as, now you have the other ones also. So A is then connected to D and D is here. And then D is connected to B. Okay. So these are the points that you have. So this was your R3 and this is your R4. And this is something where you want to measure the voltage difference at. Okay. So at the intersection of the bridge that you have. So this is like a diamond bridge. You have multiple configurations of it. This is like very basic simple one. So there are terms that people say that this is a parallel bridge and this is a balanced bridge. If you say that this network is balanced, you see that the voltage difference in between C and D is zero, essentially meaning that voltage as C is equals to voltage as D. But if it's not, then you try and make it balanced. Okay. How do you do that? You adjust the value of a resistor that you are claiming it to be adjustable. So in our case, it can be this R3. Okay. So this one can be adjustable. You can change it. And accordingly, the value of your another resistance R4 could also vary to make this bridge as balanced. Okay. So here you see that what is happening. Here, this resistor, so there's a relationship. How it comes, we'll see. So let's say I want to measure the resistance at C. How I'll do so is RC then would be something as, because it's through measured at this, so it's R2 by the total resistance over that particular series column. So R1 plus R2, okay. Similarly, for against D, it would be R4 by, R3 plus R4, okay. Now, once you have those, now to make this bridge as balanced, the resistance across these two should also be same, right? Or the voltage difference across these two should be same. So if either I have an I1 and I2 passing through both of these columns through this and this, like it's being splitted from one source current to another one. I'll have different voltage sources also. Now these total terms should be same to each other. Okay, so this would be R2 by R1 plus R2 is equals to R4 by R3 plus R4. Now, when you have, like, let's just multiply both of them, you have R2, R3 plus R4, R2 is equals to R1, R4 plus R2, R4. Okay, so this is same in both sides. So you have R2, R3 is equals to R1, R4. You can also write it as R2 by R1 is equals to R4 by R3, or you can also write it as R1 by R2 is equals to R3 by R4. Okay, so what's happening? You take this ratio of 1 by this by this. So against the voltage source that you're trying to measure, you just take the ratio of both of them. This is a condition where you say, or either this one, you say that your bridge is balanced. Okay. So that's how you compute a bridge as balanced. And what else I wanted to say in this terms? So of course this is there. Yeah. So let's say in cases where you again have resistance, let's say I have extra resistance which is being connected here, okay, something like this, and this is being given, let's say it will have some x ohms, okay, so the value for this is known, and they are trying to ask you that what will be the resistance across this particular resistor. So what you do, you first take the ratio, see if the bridge is balanced or not, and then, so that means that this is the resistance that you have across this particular arm, across BD arm, okay, and then you take a parallel difference, so you just measure the parallel resistance across both of them, and then from there you find the resistance of this particular one. Okay, so we compare both of them, the ratios of them essentially. So in here everything revolves around this formula, or if not, you always compare, you go and see the resistance across the edges, the arms that you are trying to measure the potential difference across, see the current across it, equate them. That's it, the Wheatstone bridge is all about. Okay. After Wheatstone Bridge, there were some materials for the strain gauges that are somehow important for you to look at. So in them also, what's actually more important is you need to understand, not understand, but keep in mind that which one's more sensitive, which one's more stable. Okay, so how it reacts under higher temperatures or lower temperature settings. Okay, so we have materials as one of them is Constantine. Then you have like platinum, you have something as nickel, and then you have as silicon. Okay. I didn't know for constant, so I just wrote on the whole thing there. Okay. So then you have different gauge factors from them, and then you have a temperature coefficient. So this is from the lecture slides only. If you want, the whole numbers are there. So the gauge factor is like ratio of resistances. Sorry. uh, with respect to your temperature differences. Okay, so within them, what happens is this gauge factor increases as you go from up to down, and your temperature, the ability of the material to react to changes in temperatures, okay, that increases. Sorry. So this one increases from up to down, whereas this one decreases. This one increases, and this one also increases. Both of them increase from up to down. So something that I remember from my own memory was something as this was 2 and this was something as 120, whereas this was 2 and factor of 10 raised to minus 6 and this was 2 and factor of 10 raised to minus 3. Okay, so both of them increase as in how you go from up to down. What it tells you is that this temperature material constant is very stable. Like to changes in temperatures, it does not have that much fluctuations or variations there. So we need materials like that for our own biomedical applications. We don't need something which would be very variable or very fluctuating with respect to that of our intrinsic physiological noise. Okay, so we say that this material is highly stable since it has a very low temperature coefficient and it's suitable for biomedical applications. So one of the application it has been used on is something to measure the force in our dialysis pump. Okay, after that you have platinum. Now what platinum does is platinum is being used as a load in multiple implants. Okay, so what I've heard that people use platinum teeth. They have different surrogates for teeth. Okay, you do root canal and those things. Then you have implants as that of heart. So you have coatings of platinum, nickel there. Why? Because of the temperature resistivity there. Because now you have an electrical pacemaker inside your heart, which gives you an excitation for your heart to start pump the blood through your systemic circulation, and then to do so, everything the circuitry inside it should not be overheated depleted. So hence a material as platinum is being chosen there. Then you also have platinum in this knee replacements, those arms where you have total knee replacements within the synovial fluids and up and joint to the knee joint. You have those platinum coated implants to maintain biocompatibility there. Okay, with that, then you have nickel. Nickel is something which is being used in to measure pressure across, and the most commonly where it was last used was something in respiratory systems. Respiratory systems. Okay, and then you have silicon. Like silicon is used everywhere as rubber, so you have it as to the catheter. You have it on needles, sorry, needle tip sensors. You have silicon. Where else you have silicon? Mm, silicon in biomedical applications when you try and measure the signal, let's say not in human measurement, body measurements when you're trying to do so, but you also have this big silicon proprietary rubbers, blue colored rubbers. What they do is they won't pass the energy through it. So you say in electrical terms, when you try and measure ECG of a person, you have different electrodes and you have a ground electrode to it. That ground electrode helps you sustain so that all energy passes through your body to ground and it's not backing up or it's not flowing back to the circuit. So in a way, you have the silicon rubbers which helps you to absorb that particular amount of energy so that it won't pass again, won't reflect again back to your system or signal of interest that you're trying to measure into. Okay. So yeah, so basic application of this is also in catheter tips, in pressure sensors. You have silicon as a material there. Okay. And since this is very high, so it is very highly sensitive. And it is also temperature dependent. So property of silicon change with respect to temperature. And like the term, like it starts to melt after some time. So you also need to look at those properties also. Okay. So that was all about the materials, basic type of materials that you have. Like strain gauges, and there are also types of strain gauges. I don't know if it is useful to a point, but they're like unbounded and bounded strain gauges. What these do is like in inbounded ones, you have a fixed arm and you have a movable arm. Okay. Now this fixed and movable arm, because of them, the energy loss would be very low and the system becomes very much highly sensitive. So you can use them in catheters or needle-based systems. You want to do angioplasty, you want to do small signal measurements, real-time measurements, you can do so there. Then you have something called as diaphragm. Yeah. So the flexible one is always called as diaphragm, which helps us to move. So you have this diaphragm in your body also. You have like this ribs, n number of ribs, and the 12th or the 13th rib, it's always the floating rib. So it helps you, so whenever you inhale, so the pressure inside your body, the volume inside your lungs, it increases. The diaphragm accordingly moves downwards when you exhale. So it comes up so that it helps all of your ribs to maintain in the same place. So that's how a diaphragm works. It's very flexible. Whereas if you have a bounded system, then you have two fixed rods and ends. So makes a system something as very grid. So it makes a diaphragm bounded to one position. So it's very compact and reliable. So for those cases, it's used in very rigid or rugged, robust systems. So most of the applications there follows in industrial based settings and thermal systems and heating machines, big boiler machine systems. There it's being used. Okay. Then we have silicon, where silicon can be used. So silicon is nothing but silica as a type of semiconductor. So it's also a strain gauge there. So what happens in here is you dope one channel to another channel, and this doping somehow increases the linearity of the system, induces non-linearity into there, sorry, decreases the linearity of the system, induces non-linearity into there, but makes the system very sensitive. But there's always this trade-off, right? So it plays on the stability of the system also. Okay, so what you do over here is you have this P doped piezo-resistive sensor, which changes its resistance with respect to the input mechanical energy being transferred, and then you diffuse it to the N-type silica of the Wheatstone bridge. That's why I talked about that. of the Whitstone bridge. And what happens to this process is your gauge factor is very highly sensitive. So it increases to NV. It's sensitive to thermal changes. But in that way, it makes the system unstable. So this is the trade-off I was talking about. If sensitivity increases, you lose on your stability of the system. But again, this all depends on the type of application that you're trying to look at. And hence, it has been used in robotics. So there, your sensitivity matters, but the stability of the robot will only matter if you try and exert it to after a particular degree of freedom. So that's not what people do. They maintain the robot within a very limited range of limit, only for biomedical applications if you're talking about surgeries and all. Okay, so robotics, and then you also have some miniature based systems. So in these settings, you use the silicon based things. Okay, well, of course, these are very expensive, not cost effective at a point. Okay, so after silicon, you have something strain gauge. So after strain gauge, we have something that is known as thermistor. Okay, so let's take a break, I guess 2-3 minute break. Do you have any questions? Okay, so a thermistor, it's a ceramic material, okay? So you might have heard about this thermostats which are there in, I don't know if it's there in Indian setting. Like I have seen a thermostat at my workspace wherever I sit and study in my office at IIT Gandhinagar. But like you might have heard it in your class 9 or class 10th in environmental or science books where there's like a sensor or a setting which increases the temperature to a point, and there where it sets to that threshold point. After that threshold point, now if it's being decreased further to a point, then it starts decreasing to afterwards. So this is a kind of negative feedback loop which is being playing there. Okay, so it works on the threshold that's being set, and it tries and see what's the optimal temperature value or the pressure value which is being set. So in this case, if we're talking about temperature measurements, it's a thermostat. Okay, so here also, it's something called as thermistor. It's same application. It tries to measure the temperature of your system. It's based on a ceramic material. It's being used for a very narrow, or you can say a very limited range of temperature measurement. Well, with that, like if it's only narrow, measures on a very limited range of temperature, it would also have its own advantage, right? So it measures very fast and it's very small. So the response time is also very fast and it's very small, meaning to say that you can use it in very quick surgeries. So you can attach it to catheters, you can attach it to needles and do the measurement. Since it's this small, it does not have anything in there, it just measures the temperature at a point and will reflect it back. So it does not need any compensation or it does not need any calibration. Okay, where you have other type of sensors which are being linked in series or parallel to each other. In this case, it does not. So you don't need to compensate or calibrate at each and every time. Okay, so how it occurs is like how you see this thermistor is, you can see it as chip. You can see it as, I guess, rods, the small length rods. There are also beads of thermistors. This ones I've looked at, this ones I've looked at. I've never looked at rods, but there is also a type of rods in there. Okay. Now, being said, so this works on a negative temperature coefficient based method. So if your resistance increases, the temperature decreases. Right. So if and more number of current is being flowing through it, the resistance increases. In a way, it tells the temperature to decrease. Vice versa. Temperature increases, the current flowing through will also decrease, and the resistance will decrease. Okay. So that's how the negative negative temperature coefficient rule works. Okay, so it's nothing but based on of this negative feedback. Okay, so for this also it's being defined, but I guess there was a small typo in the equations that were there in lecture sessions. So something like this was written, that how a thermistor's resistance is being defined. RT by R naught is e to the power beta times T naught minus T by T naught. Okay, so in here, only thing was that this is 1 by T minus T. Okay, so what comes as T naught minus T by T naught. So a term of T is missing from here. If you would have tried to derive it, you would have got it. If not, this is why you didn't get it. Okay. So, yeah, so in lecture, Prof has derived it. If you want, I can derive it for you. Simple first order differentiation. So you have this RT by R naught is equals to exponential of, let's say, beta times 1 by T minus 1 by T naught. Okay, so if you just see it, the one is RT is equals to R naught times e raised to something which is a function of temperature, right? Because Prof said that you first derive it with respect to temperature and then you divide it by resistance, right? So what we do here, so since we are trying to differentiate, so del R by del T is equals to, you have your R naught e raised to ft, and this will follow a chain rule, right? So you again have a derivation of your ft here, right? Since you have this, so sorry, this is capital T. This is also capital T. So now you want to differentiate this del F by del T. Now this is constant, right? So d by dt of 1 by T naught is 0. But this is dependent on T, right? So d by dt of 1 by T is what? So you have x raised to n. How you differentiate it? You have nx n minus 1. Okay. So this would be minus 1 by t square. Okay, like this. So you have this one. So what do you write here is, and this one, if you see this whole term, what is this term? Essentially, or this part that you wrote, right? This one, your fig equation 1. So you can substitute it here. And you can have RT times, what is this? Beta. Oh, sorry. Was it beta? Yes. Times minus 1 by t squared. Okay, so this is equals to RT minus beta by t squared. Okay, so this you represent it as del R by del T, or you can also take it back here. So that becomes 1 by RT, and then you have dRT by dt is minus beta by this. So this is how your um, change in temperature relationship with respect to resistance is being defined. So this is your that coefficient that you're trying to measure. Okay, so yeah, so that's how you get this relationship. Only keep in mind that you have an extra t in here, so that t was missing. Okay, so in here, you see what's happening is you have a dependence on exponential, right? Everything is exponentially changing. Since it's exponentially changing, what is the system? It is non-linear. It's no longer linear at a time, but it is highly sensitive, right? Sensitive. Okay. And then you have different type of sensor, that is resistor temperature detector, something as RTD, which is linear. But here it is non-linear within the resistor temperature curve because it has an exponential within it, right? Because of this exponential of it. Now you can achieve linearity here How do you do so? You can have a resistance in parallel of the thermostat that you're trying to measure, or you can have a resistance in series of the thermostat that you're trying to measure at. If you have it at parallel, you can have this as adjustable. If you had it in series, you can increase the load, and since load increases, your deviation will be minimized. Your current passing through it will also be decreased. So your noise in the overall system will also decrease. So your system in a way can be linear, but you can achieve linearity using this, but the system inherently is non-linear. Okay. Okay, then there is RTD. So RTD is something which people use to measure long time measurements. So thermistor can be something as, okay, you do a quick measurement, you like insert in your mouth and keep it for some time, or in under your arm and you measure it. Whereas you have something as RTD, resistor temperature detector. So in that you measure it over prolonged time. So that's a very linear kind of measurements. And what happens in RTD is your resistance of the measurement at a particular time is dependent on the change in temperature there itself. So it's very linearly proportional, that system. So you can monitor it over long time, and these RTDs are metal. Okay, these are metal. That was the detail, that's what's needed. Okay. Next is capacitive sensors. Okay, I guess we only have 15 minutes. So let's just go through the equations very quickly. I had many notes pending. I'll just upload them online. You can have a quick look on them. And perhaps in next class, we can look at piezoelectric and electrochemical and optical sensors. We'll go through the assignment very fast, quickly, okay? We'll give 30 minutes for assignment questions. Okay, so capacitive sensors, these are the ones which are separated by dielectric membrane. You have two displacement plates there. You have an insulating membrane in between both of them. So you define it as two dielectric constants, let's say first one and second one. Second one, and then it's dependent on the cross-sectional area and the displacement in between both of them. There's also a sensitivity factor for capacitor, so you differentiate it with respect to the displacement or the distance in between the plates that you're trying to look at. So it is so similarly, you have delta x at the bottom. So how will you differentiate it as? It will go up power minus sine and x squared. Okay, so that's how you do that. Then you can also measure the displacement at a time. How do you measure displacement? Let's say you have two capacitors with you, and then you know the area for one. Let's say it's area 1 divided by the thickness will remain the same. You have area 2 and displacement remains the same. So your area is nothing but essentially multiplication of the width and the thickness of your plate, right? And this can be your width and can be the like entire capacitor is of a length L, right? So if one is something and another one can be n minus x. So you can then write it as epsilon width d. You can have as this will come out. So you have this R L minus, I guess I wrote something else. So this is 1. Let's keep this as 2. So everything that will come out would be 2. And this is like difference with an X. Okay. So that's how also you can measure displacement. Okay. I guess my laptop is on low battery. Then with capacitive sensors, of course, since one end is fixed, another end is moving, you have a diaphragm. So the system is pretty much flexible, but based on the flexibility of the diaphragm depends on the stability of the system, the sensitivity of the system, and the noise that you can have. So everything all in one would be a package where you can afford some, you cannot. The other properties will also change accordingly. So if you change the diaphragm there, the separation between them will be reduced, and hence the separation is reducing. So your thickness is changing, which is on the denominator side. So hence your capacitor will increase there. Okay. With that, we have inductor sensors. So previously I told you that what inductive sensors were all about. One, you have a self-inductance, other you have mutual inductance, and then you have a linear variable differential transformer, which works, has a primary arm, has two secondary arms, and it changes across the null point where you're trying to measure them. So the operation here is very frictionless. What else? Self-inductance, it's a very, you change it one coil and another one is movable one. So it's a very simple operation, but it's non-linear. Then you have mutual inductance where the relative moment in between the two coils will change the inductance there. Okay. So I don't think so there's much in inductance, but I guess the formula I can give you right here. So the inductance is your number of, sorry, turns in a coil times your geometric form factor times your permeability of the medium divided by the length of your coil. Okay, so let's just write this. This is number of turns in your coil that you're trying and wounding around that particular magnet that you're trying to do. Then this is your geometric form factor. So basically the area that you're trying to look at. And then you have a permeability of the medium. And you have a length of your coil across which you're trying to measure. Okay. So we'll look at the others later. If in assignment we come through questions which we didn't go through, then I'll of course help you there. Any questions till now? I guess we covered pretty much everything. Any questions? Okay. So if not, let's go into the assignments. I guess that's what all of you are also waiting for. Let me first save those notes that we had now. So taking some time. Saved. Where did it go? Okay, that's it. And we have assignments. Okay, so let's go. It's you answering. I'll just wait for 2-3 minutes. You can answer the question. If not, then we can always discuss. Okay. So what's the sensor? We discussed this at the beginning of the class itself. Something which detects sounds, produces signals, provides usable output, or converts energy to energy.
Third one.
Yes. So it's a device that provides a usable output in response to a specified quantity which is being measured. In our case, it's a physiological signal. Okay. Resistance of a thin wire is given by what formula?
Third.
Yeah, that's rho L by A. Here, the capacitance of a piezoelectric sensor is this. This is picofarad. Okay. Its sensor leakage resistance and amplifier input impedance. So the leakage resistance and the amplifier input impedance. Impedance is given by Z and I is input. Calculate the low corner frequency of the system. So I'll tell you two things. So in a system like this, in an amplifier like this, you have this sensor leakage resistance and this amplifier input impedance as parallel. Okay. And afterwards, you know for capacitance, you have the corner frequency formula as 1 by 2 pi RC. Can you try? Right, so anyone got the answer? So here, one is your gigaohm, one is your megaohm. There's a power of 6 difference in between both of them. If you take it inverse of this one, plus you do for 16 megaohm, this is very much near to zero because it's much larger than that of 16 megaohm. So that's why your R equivalent, you can directly take it as approximately as 16 megaohm. Now you can compute your 1 by 2 by 16 mega ohm times your capacitor as 325. Convert this pico and then farad, because everything you want to have in SI units, because this is in frequency, hertz. So what would be our answer? This. Which one? Can do the calculations. Hmm. Sorry. Okay, so let's do the calculation. You have 2 times 16 times 325, then 6, and then minus 12. You have 6 going up. So this all is something as 5.2 10 raised to minus 3. Okay. Your 2 pi RC will be 2 times 3.14 is 0.03267. You do 1 over that. What's the answer? It's in hertz because this is seconds. This is 30.6. Okay, so 31 hertz. Okay. Everyone, we are on same point? This was okay? I guess yes. Okay. In thermistors, which are used for temperature measurements, the resistance temperature relationship is what? Is it linearly and positive correlated, exponential, and shows a positive temperature coefficient, linear, inverse, exponential, negative temperature coefficient? Which one?
Negative temperature coefficient. Exponential with the negative.
Exactly. And next, what's the significance of a glass coating on a thermistor? So a thermistor will always have a glass coating. You might have seen this thermocouple is not thermocouples, but the thermometers that you have, like, so they are all coated with glass. Will have some liquid or chemical inside it, but a glass is there. For the same, the thermistors do also have a glass. So why that glass is exactly present there? What it does? Will it alter the characteristics which makes it suitable for high or low, or will it increase the conductivity of the system, or will it protect it from environmental factors not affecting the thermal response of the system? What it does? Anyone? So, of course, it only protects the thermistor from environmental factors so that it won't affect the thermal response of the system. So that way, this glass and the material of the glass, the temperature at which this glass interacts should also be concerned. So the type of film, the thickness of the glass that you're trying to add there also matters. So people who are in material chemistry, they also look at these things. Okay. Now, when a static load is applied to a piezoelectric sensor, okay, a static load, what is the primary reason for charge leak? It leaks due to low capacitance, through the leakage resistor, through a high internal resistor, or due to parasitic inductance. Well, we are talking about a piezoelectric sensor, which is the first option that you'd like to eliminate here. Any guesses? Well, wrong answers are also fine. So that we'll know that this is a wrong one.
Through leakage resistor.
Sorry?
Charge leaks through leakage resistor.
Exactly. So, well, of course, that's our answer. The first option that will eliminate is this one, and that it leaks due to the parasitic inductance. So, we have a piezoelectric system, it won't have an inductive based component there. Next is a static load is being applied. So, because for a static load, we won't have a high internal resistor there in the system. So, this is also gone. Then we have a piezoelectric sensor, charge is leaking, but a capacitor and resistor are both things which are possible. Now, resistor is the one through which your charge can be leaked because capacitor is the one which stores the charge and it will discharge it once your system's load become a dynamic. Okay. Sorry for the disturbance. So I answered here is charge leaks through the leakage resistor. Okay. Question 7. In a capacitive pressure sensor, on what values do the deflection or deflection of the diaphragm depend on? So you can just remember what you have in capacitance. You have this dielectric constants, and then you have the area, and then you have the thickness. Okay, so on what all things the capacitor of the pressure, this thing values depend on?
Thickness, radius, and pressure applied on the diaphragm.
Exactly. So you don't see a pressure in this equation, but of course, these dielectric constants are the one maintaining it and also the area in between the plates. Okay. Now, the typical value for K for quartz, so this is that sensitivity factor, which comes from your piezoelectric sensors or either from your capacitance systems also. So here, the values, I don't think so you should remember it, but it's 2.3. The unit stands as pico coulomb per Newton. Okay. So that's how it is being there for piezoelectric sensors, piezoresistive sensors. Okay. Which of the following can be used to measure the change in displacement of internal organs? So keep in mind that this is a very broad question. Okay. There are two answers to this question. But just keep in mind that we are trying to just ask that to measure the change in displacement of internal organ, it can be any organ. So we are not focusing on one particular organ and saying that, okay, this can be also the case, because the question has two answers. So only one answer is the one which falls for this question.
Ma'am, one answer is differential transformers sensors.
Yeah. So one is this, but the actual answer which NPTEL team gave was mutually induced sensors, because this is a subset of it, right? And differential transformer sensors are being used for a very limited narrowband range. So they can be used to measure or sorry, where the sensitivity we want it to be higher and enough, where your system has a three-play role. But for all organs, you will only have relative motions in between only two systems being played. If it's our respiratory systems, you have different ribs playing. If it's a heart, you have valves playing at a time. So that's only two. So it's mutually induced sensors. Okay. But answer is also differential transformer sensor. Okay, last question. What's the advantage of connecting two secondary coils in opposite direction? So of course, this is for this LVDT, huh? Sorry, I didn't mention. So, and the question also does not have anything, but in LVDT, since you have a primary coil and two secondary coils, so what happens if you connect two secondary coils in opposite direction instead of having them in one serial direction? So of course, you also know that the system is very highly non-linear. So it can do either this. Which one? Any guesses? So you might remember that we did something.
To achieve maximum linearity, ma'am.
Exactly. To achieve maximum linearity. So having these two secondary coils opposite to it or in parallel to it will do nothing to your power consumption. Well, it will essentially remain the same, but it will play with its stability. Okay. Then the next option is easier wiring. Well, no, if you do so, it's only difficult because series is always easier. Okay. And better resistance to noise. In this LVDT itself is a differential transformer, so it will create huge amount of noise, and that's a trade-off that we need to play with. If we make the system more linear, then the noise, it's very easier to suppress it along through digital signal processing based methods. So this is also like a sort of 50-50 based answer. So it's just to achieve maximum linearity in the system. Okay, so that's it for today. If you have any further questions, you can stay back and ask me. I'll be in the session for 10 more minutes, like till 12:30, and then we'll close it off. We'll meet this Tuesday again, 6 to 8 for week 3. Thank you. Any questions?
This session is uploaded in NPTEL portal.
Not in NPTEL portal, but you'll be given a sheet. I guess I can show it to you now. I hope my screen is visible to you now.
Yes, ma'am. Not visible.
Not visible? Let me reshare. I guess now. So you'll be given this sheet, and within that sheet, you have access to the YouTube link. So this is the link where the recording of this lecture will be uploaded. This is the link where you'll have all the lecture contents. So the lecture notes that we just had, the assignment that we just solved, those would be there. Of course, if you want, I can also write the derivations for it or solve them, but we solved it together. So these things are already here. And then, how do we move it? You like just me and the number of people join. So you can access it through this and this folder. So this would be shared to you on your portal, but on my side, the portal looks like this. I don't know how it is on your end. So you'll have to cross check it. Probably it will come through your announcement page. So this is for last year. You'll have it for this year. So that content difference would be there, but would be somewhere in your announcement page only. Okay. To go back. Stop sharing. Okay. Any other questions?
Thank you, ma'am, for teaching us.
Okay, it's fine. Thank you. Okay, so if you don't have any further questions, like people who have questions can stay back, or else I can close this session in like 5-10 minutes. So, thank you.
Ma'am, can you please little bit explain about pacemaker?
Yeah, of course. So, you know, why a person needs a pacemaker? He or she will need it when so in your heart, there's a sinoatrial node, which is responsible to make this first excitation so that your entire electrical activity within your heart starts from. And then it will send signals to your other fibers and muscles and valves so that arteries, they can squeeze in the blood to the ventricles, and then ventricles do so and goes to the lung, comes back to the atrium again, and then again to the ventricles, and then to your whole body. But when the system is getting hindered, so your SE node is not working at a point, then you need a pacemaker. And this pacemaker will act as a secondary SE node, and it will be the one to initiate that electrical activity. When it does so, that at that point, your other fibers, other nodes in the muscle, in your heart, they'll get this electrical stimulations, and then your blood flow will start from there. So that's how a pacemaker works. Of course, it's an electrical instrument. It has its own lifespan. So it's an electrical equipment also. So you cannot go and have MRI. So people with pacemaker have that issue. And then there nowadays they are trying to make it MRI compatible, having a magnetic insulator in front of it. The material should be as such, but it's still in process, still in research. Material people, chemical people. I guess even in a mechanical side, they're also working on it. How to make it very compact. Even electrical people are working on it. How to make it very single, reusable, only attached to one part and not having these two electrodes jumping outside. So people struggle with it. Like you cannot sleep properly. You need to see your breaths per minute. You need to check over time your blood pressure because everything changes with it. Essentially, your each like the type amount of volume that your heart is beating into your entire body for all the organs to work at a time is dependent on it. So it's a very essential system into your body when you have so we need to take care of those peoples, and we need to be very sensitive in those cases if you have people with pacemakers around us.
Thank you, ma'am.
Thank you. Okay.
Hello.
Anyone?
Good afternoon, madam.
Good afternoon.
When you take the electromyography, what
Mhm.
exactly we are measuring?
So when we are doing an EMG, we are trying to measure the potential differences that are coming out from our muscles, different activities. So muscle in a way has many noises, and you have this voluntary, involuntary muscle activities, right? So people try and measure what happens or what changes in your flexus if you do an extension, if you do a flexion extension procedure, if you rotate your muscles, try and see. So in some cases what happens is they'll lose their some motor activities, their reflexes won't happen at a time. You have stroke, you have Parkinson's because of that. So EMG helps us to measure those muscle potentials at those points and accordingly provide stimulus to those patients so that their activity can be restored.
Like when you measure the ECG, PQRS voltages are measured, and when you measure EEG, alpha, beta, theta waves are measured. In EMG, what exactly we measure so that we can say the abnormality and normalcy? What quantity you are measuring?
Muscle potentials, I don't think so. They have like they are being quantified. But what I know is the only thresholds and levels of EMGs are being quantified. Like because the data that you get in EEG is of course noisy, but in muscle it's whole to an other level because you're trying to measure almost everything at a time, and it's again surface level. You cannot do invasive measurements of EMG. It's all surface. So it's only, I don't think so. It has only like specific terms for that. Let's just Google it if we have any.
Any
EMG.
graph is it called EMG? We call as a graph now. Is it any graph or waveforms are generated? Can you see like graphs or
Yeah,
EMG?
of course. Yeah, yeah,
Yeah,
yeah. It's very similar to
yeah,
that of EEG. It's just the
yes,
voltages, millivolt differences you see. But of
yeah,
course,
mm,
EEG voltages are on microvolts level,
yeah,
whereas EMG are on the order of volts because you get many movements, many involuntary movements there. So the amplitudes like they shoot at any time, and you really need to differentiate the noise from them. So that's how
yeah.
people working in Coxside, people working in mechanical civil engineering work with.
Okay, thank you, madam.
Okay, thank you everyone then for joining. I'll see you then on Tuesday, 6 to 8. We'll discuss more on week 3. We'll also cover the other 3 type of sensors that we missed today. We'll look at the Hall effect, we'll look at piezoelectric and resistive sensors, and the electrochemical optical sensors. Okay. Thank you for joining today. Thank you. Bye-bye.